Now that we've taken a look at what numerical integration is and looked at one of the methods called the trapezoid rule, we're going to look at a more sophisticated method called the Simpsons Rule, which is going to use polynomials as the top of the shape that's the subinterval to numerically integrate. So let's talk about Simpson's method, and it's named after English mathematician from the 18th century, Thomas Simpson, who used this to calculate more precisely the area under a curve. And what's unique about Simpson's method is that instead of using a line between 2 points to approximate the top of the interval, the height of the shape, it actually uses a second-degree polynomial. For example, in this picture from Wikipedia, the blue shape is the function, and the red is the Simpson polynomial that approximates the function. If we have one interval from A to B, we can approximate it through 3 points, a polynomial of degree 2, a parabola that travels from A to a midpoint to B. And so using this second degree function, this parabola, to connect the left and right endpoints, turns out really generally does a very good job of figuring out the area with a very few number of even subintervals. Now it does have to be even because, as you can kind of see here in this Wikipedia picture, it takes 2 subintervals to make one Simpson polynomial. So let's look at the theory and the application of Simpson's rule on the function f of x equals x to the third minus 2x squared plus x plus 3, which is the function we used to evaluate using the trapezoid rule in the previous screencast. We'll see if Simpson's rule can do better. Intuitively, we would think it could, because instead of connecting by trapezoids, we are going to connect using parabolas between the points. So since a parabola can be written in the standard form ax squared plus bx plus c, and this is capital A, capital B, and capital C, not to be confused with the endpoints of the shapes. But if we integrated that, we would actually find the area under that red curve between x1 and x2. x1 being the left bound and x2 being the right bound of our interval. And when we do that, we would get 4/3 ax to the third plus 1/2 bx squared plus cx, the fundamental theorem of calculus, and substitute x2 and x1 in. All that math is beyond the scope of this course. But suffice it to say that when you finish simplifying a lot of math, the area of one of these Simpsons rule shapes is going to be b minus a over n times 1/3 times the very first left function point plus 1/3 times the far right function point plus 4/3 times the middle of the function point. And if you added up all the different Simpson rule shapes underneath this curve from 0 to 2, what you would get is b minus a over n times 1/3, because we could take a 1/3 out of each of these, so the 1/3 times the first f of x0 plus f of x4, plus an interesting pattern emerges because of the way the terms in the different areas combine. In this case, f of x2 appears twice, so f of x2 actually is 2 times that, and f of x3 and f of x1, because they only appear once, but they're multiplied by 4/3, we put a 4 in front of them. And again, I took the 1/3 out of all of them. So an interesting pattern emerges, and in fact, this works for larger Simpson rule shapes where there are many more subintervals. And if we put the 3 and the n together in the denominator, what we have in simplified form is what's called Simpson's rule. The area under the curve can be numerically integrated, numerically approximated by b minus a over 3n, and again that 1/3 comes from this integration up here and appears in all the terms after a lot of math. So b minus a over 3n times the first term f of x0 plus the last term f of xn, whatever that is. In this case n was 4, but in the general sense it's just x of n. And then this pattern of 4, 2, 4, 2, 4, 2, beginning and ending with 4 in the middle terms emerges. For example, 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3, ... Okay? And then we get to the second to last even term. It would be 2 times x of n minus 2, which is an even term, plus 4 times the last odd term plus the last term. So the pattern is first and last only appear once because they're only used in one of the shapes. All the odd terms have a 4 by them because they're actually only used once. And all the even terms appear twice, and so they have a 2 in front of them. So let's apply that to our situation here with n equals 4. And so we have 2 minus 0 over 4 times 3 times, so that's the delta x times the number of subintervals, times the first f of x, which is f of 0, plus the last one, which is f of 2, f of a and f of b. And then our middle terms go 4 to 4, beginning and ending with 4. It's important to note that Simpson's rule must be used with an even number of subintervals. Otherwise, we won't have this 4 to 4 pattern and it will break down. So this x1 is f of 0.5. x2, which is multiplied by 2, it's f of 1. And then x3, which is multiplied by 4 because it's an odd term, is f of 1.5. And when we add those together, combine them together, the area using Simpson's rule with only 4 intervals, 4 subintervals, is 6.673. And you'll recall that the actual area you can get through definite integration, the exact area, is 6.66 repeating. So we're really off by only 7/1000ths of a unit squared with only 4 Simpson's rule subintervals. Pretty darn good for only n equals 4. So even though it's a little bit more complicated to set up, and it's more complicated to derive, unfortunately beyond the scope of the screencast, but with just a little bit of extra work, you get an answer that's far more accurate, and you can kind of intuitively see that with the curves there using Simpson's rule. So that concludes our exploration into numerical integration using the trapezoid and Simpson's rule to numerically integrate functions that we cannot analytically solve.